Hi, this is Dave Johnson with another edition of Math Off Topics. In an earlier video, I showed how the formula for a derivative at a point could be derived from a linearization of the function at that point by doing a little bit of algebra. And so I'm going to do the same thing now for functions of two variables, and we're going to get the formula for the partial derivative, and this process can be generalized to functions of any number of variables. So let's get into it. So we start with a power series uh, expansion of the function. So here's our function of two variables, and evaluating at the point a comma b. And here's our first derivative or with respect to x, so partial derivative with respect to y. And we're only taking the first few terms. Beyond that, we have what we call the error. So this part here is the linearization of the function near the point. And in fact, for functions of two variables, we know that that's a plane that's tangent to the surface of the function. And so what we want is that the error goes to zero a lot faster than the distance to the point a comma b. And one way to express that mathematically is to say limit as our point approaches a comma b of the error divided by this distance. And notice I'm just using the Euclidean distance between the point and our a comma b. We want that ratio to be zero. And the only way that a limit can be zero like this is if the numerator goes to zero a lot faster than the denominator. And so for our purposes, we're going to assume that for a and b close to, or xy close to ab, we're going to set this error term equal to zero. So let me go ahead and do that. So uh, we're going to say that the error of x comma y is equal to zero. And what that implies is, now let me go ahead and solve. So f of x comma y minus f of a comma b is equal to the partial derivative of with respect to x evaluated at a comma b times x minus a plus the partial derivative with respect to y evaluated at a comma b times y minus b. Now, I should point out that um, we're using the partial derivatives, but we're pretending like we don't know how to calculate the partial derivatives. So the partial derivatives are some measure of rate of change here, and we're multiplying that times this separation between x and a and y and b. And so but what we're going to try to do is come up with the formula for calculating the partial derivatives. Since we're talking about partial derivatives, let's assume that x minus a is equal to h, and that h is going to be small. So small h, and therefore x is equal to a plus h. And we're also further assuming that y minus b is equal to zero. In other words, we're really dealing with partial derivatives here. So therefore, y is equal to b. And what we can do is go ahead and plug this in. F of a plus h comma b, because y is equal to b, minus f of a comma b is equal to, and then this term is going to be zero, but let's copy down that first term on the right. So f sub x evaluated at a comma b times x minus a, which we're going to just go ahead and call it h. So times h. Now solve for f sub x evaluated at a comma b, and that's equal to f of a plus h comma b minus f of a comma b, all divided by h. But this was only true for small h. So in other words, the smaller the h, the more accurate the approximation. So that's the same as taking the limit. So we can rewrite this f sub x evaluated at a comma b is equal to the limit as h goes to 0 of f of a plus h comma b minus f of a comma b all divided by h. And we can get a similar result for the partial of f with respect to y by assuming that x is equal to a and that y minus b is equal to h, and go through the same process again. So I hope that's been helpful. If so, please like and subscribe, and I will see you in the next video.